Okay, so we're almost at the end of virtual work. Now let's have a look at example number 9. So as noted, it is an exploratory level problem. So if you don't want to tackle it, don't worry, just move on. There's a video that goes through the full solution for this one here. So there's a bit of algebra involved, or a bit of calculus involved. I'll just try and get the principles across for this one here, just by perhaps doing a simplification. So the simplification, in this case would be, let's try to solve a simpler problem. So the simpler problem might be this case here, where we've got a simply supported beam with a load in the center. And we've looked at something like this before, right at the start, when we use virtual work to calculate the reaction at that point there. So in this case here, we would say, to simplify the question, we would say, let's calculate the bending moment at that point under the point load, and we'll call the bending moment, just label it A, B, and C. So we'll just call it MC. So now, so we've labeled it MCB, and we now want to use virtual work to calculate the bending moment at C. So what I'll do here is that I'll draw out the virtual side, and this time here, at the position where we're trying to work out the bending moment, I will say that we're going to bend it, so like a mechanism, so that would go up like that. Okay. So if you remember, in the second example, right at the start of this section here, we broke equilibrium and we moved it up by 1 bar. So in this case here, I suppose, well, I'll just call that H. Okay, so H, I was tempted to call it 1. Okay, but we'll say, so in the previous question, we were trying to use virtual work to work out that reaction. And then we move that up by 1. In this case here, we're going to do something like that. Now let's go back to our expressions. So we've got internal virtual work is going to be equal to the external virtual work. And then here we've got a load P acting on it. So the external virtual work, of course, is going to be this P, and that's moved by a distance H. So the external virtual work in this case is going to be PH. Now the internal virtual work, there's a bending moment at that position, C, which we're trying to calculate, and that's also done some work. And it's done some work here in that it's rotated. So if you imagine this used to be a straight line, now it's gone through a rotation. So it's like taking a ruler, I suppose, and just bending it and forcing a rotation through with this with this displacement H. So if we said that was theta, and then that was also theta, then we could conclude that this angle here is going to be 2 theta. So we've come up with some angles, and then the bending moment at C has done some work, or the moment at C has done some work, and so I'll call that MC. Bending moment at C, and it's done some work, and that work is done to theta. And you get 2 theta equals P over H. Now let's do some stuff here. So we've got sine theta. Remember, this is a very, very small displacement upwards here. So in the previous question, we put the displacement up here, but now we're putting it there. So it's a really, really small displacement. So sine theta is approximately equal to theta, which is approximately equal to L over 2, which would be that distance there. Okay, so that would be L over 2. So sine theta is h divided by L over 2, and that's approximately equal to 2h over L. Okay, just by some rearrangement. So we've got theta is approximately 2h over L just by some geometry. So substitute our thetas back in and we get MC, which is the bending moment, has done a rotation of 2, so times 2 times theta, which is 2h over L, and that's going to be equal to pH. So pH, so obviously the h's are going to go, and then you get 4mc, mc is the bending moment at C. 4mc over L is going to be equal to P, and therefore MC is going to be equal to PL over 4. Okay, as the bending moment. So so some things that you don't really need to worry about. So you could see maybe that P is going in the opposite direction of H, so technically speaking there should be a negative, but that's not going to make any difference to the absolute value, and we know that this this bending moment is going to be sagging. So if we just did it the old-fashioned way, which would be statics, you get P over 2 times L over 2, and then that will give you the bending moment there, P over 2 times L over 2, and then you get MC, which equals PL over 4. Okay, so this is the way to do it by statics, and then you can see that we've been able to get something similar just by equating internal virtual work and external virtual work. So now you could say, let's make the problem a bit more complicated. So I'll leave you to try this one for yourself. So the next step would be to look at this beam here with the load P going downwards, okay, as before. And then this time we might say we want to get this bending moment at that point here, which I might call MD. So that would be A, B, C, and D. So this time here we might want to get MD. So if we want to get MD, then on the virtual work side, we would be sticking a mechanism. We'll make the D go up by that distance H. Okay, so we'll break equilibrium there, and that will go up by this distance H. And I suppose you should be able to do something very similar, which I don't really want to do for you here. But you will get internal virtual work is going to be, you have to work out what these angles are. So you might call this theta, you might call this beta, and then that would be theta plus beta. And you'll have enough information from the different distances to be able to work out equations in terms of H and L for theta and beta, add those two together, and then the work done on this side here, the external virtual work, is going to be P times H over 2. So if you can handle that, then you should be able to handle that, and you'll be able to work out that the bending moment is PL over 8 at D. So I'll leave you to do that calculation. And then once you've sussed all of that out, then the next step in the complexity is to say we've got the same problem, but this time we've got a UDL. And we also now want to work out this MD. So So you should be able to do that one, and then you should be able to do this one here with some integration. And there's a video on the Dropbox. So as I stress, this one here is an exploratory level problem. So please don't feel bad if you don't really want to try it. You can just leave it, and you're not going to fail the exam if you can't do such problems. Okay, so that's the exploratory level problem. Okay, let's move on. So there was a question on Piazza that asked me the effective shear area and where does the 5/6 come from. So it comes from there, the effective shear area, which is Appendix 1, effective cross-section areas for shear virtual work and deflections. So just bear that in mind if you're wondering where the 5/6 comes from. Here we've got the Appendix 2, which you can use in the exam. To work out the areas of the parabolas or the cubics or just a straight line, which would be this case here. And then here, tabulate it nicely for you, is the position of the centroid of the shapes. So you can just read that off if you wish to use the graphical method. So here are some problems that previous students have talked about. So first one is calculating degree of indeterminacy. So I hope this one is already okay. There are equations that you can find in textbooks that will calculate for you the degree of determinacy. But generally, generally, if you follow the equation, you could get a problem that the equation can't really tackle. So it's best to have an understanding yourself so that you're not reliant on the equation. And I can't even remember the equation myself. So when you look at this one here, you could say, you should all know this, if there was a simply supported beam like that with a load going on it, that would be statically determinate in that you can use statics to work it out. If you stuck another overhang there, it would still be statically determinate. And then if you added another one, then another support condition, then it becomes indeterminate. So that would be statically indeterminate by 1, okay? And similarly, if you added another one here, then that would become statically indeterminate by 2. So a simple way to calculate the degree of indeterminacy of a structure is to count the number of reaction forces in the structure and then subtract 3 from it. So 1, 2, 3, 4, 4 minus 1 is 1, and degree of indeterminacy is 1. And then if you've got this one here as an additional 1, then 1, 2, that being the horizontal one, 3, 4, 5. So with this one here, it would be statically indeterminate by 2. So that's how I would normally do it. So this one here would be statically indeterminate by 2, and this one here would be statically indeterminate by 1. So that's just a question that came up on Piazza before, and this is a student explanation. So this one is a triangular distribution load. I think we've covered cases, we've even covered some in-class examples to work this out, where that is a W. But what happens if there's a variation? What happens if there's a variation of W? So if there is a variation of W and it's not constant, but it's a triangular shaped distribution, then that would lead to a cubic function for the bending moment diagram. So that would be a cubic function. So, and of course for the virtual side, you're just applying the force at the center, as you can see there, so you can work it all out. So for this sort of problem, I think we would like you to be able to identify that the correct method to do this is direct integration. and that if you use the tables, if you use Appendix 3, then Appendix 3 won't work. So if you try to use Appendix 3 and try to use shape 10, then that one's a quadratic, not a cubic. So that would be an approximation, but it wouldn't be the same. So so using direct integration is the correct way forward. So here we've got the virtual moment, and then here we've got the real bending moment diagram here. And then you just put in the two functions. So he's clearly doing it by half and then multiplying it by 2. So clearly doing it half from 0 to L over 2 and then multiplying it by 2. Put the equations in and then solve the integration, and then out will come the WL4 over 120 EI. So try it using this one here, and you'll see that it doesn't give the right answer. And try and understand why. And explanation is that this is for this table is just for very normal shapes like for a UDL. Okay. So for something like this, use direct integration. So here we come to Appendix 3, and then after that, virtual work problem sheets. So a series of problems for you to work through or look at the solutions for. So these would be the basic problems. This one is similar to the past exam questions. This one, yes, I would like to think these are all quite straightforward. Here's the one that we just talked about here, for the where the UDL is a triangular shape. Find the bending moment, and then exam questions. So these would be, so you can see that one's come out in the exam before. This one's come out in the exam before, similar to earlier problems. Again, similar to earlier problems, similar to number 7 that we've seen. So here, just some questions that previous students have asked before about. So this one's about the positive or negative, and as long as you're consistent, you don't need to worry about positive or negative. As long as you're consistent with your workings, the maths will sort it out. And then I endorsed that solution. Determine the, so this was one of the ones that I worked out before, so you can see I'm using the appendix here, virtual work problem P15-5, and then the truss ones here. So you can work through all that. Okay. So now we're going to be starting the next section of the course, which is the analysis of statically indeterminate structures using the flexibility method. So if you look at the past exam papers, so you'll have, I believe, 3 hours for your exam, which would be online. So question 1 is always slope deflection method. Slope deflection method plus the qualitative analysis. Question 2 is shear or buckling, or both. And then question number 3, it's virtual work or unit load method. Or flexibility. So one of the things to remember is that the flexibility method, it requires the use of the unit load method, okay, to calculate deflections. So when this section, bear in mind that you will not be able to do much in this section unless you are quite okay in how to how to use the unit load method to calculate deflections, as we've talked about in the previous section. So again, some good textbooks, which is the Megson book, of course, where these course notes are taken from. So Megson, and gives the page numbers where it's taken from. And then the prerequisites for this, of course, free body diagrams, all the stuff that we've done in section 1 and 2, concept of equilibrium and calculation of support reactions, axial shear force and bending moment diagrams in beams and frames, which we've already covered, solving forces in truss members, which you would have done in first semester using the method of sections and method of joints, competence in using unit load method for calculating deflections in beams, frames and trusses. So we've done that. We've done that already, and concepts of competency in basic matrix algebra, matrix vector multiplication, matrix inverse, and solving systems of simultaneous equations. So if you recall, the slope deflection method, it's a hand method. Meaning that engineers in the design office could possibly be using the slope deflection method, and you would be coming up with simultaneous equations. So simultaneous equations. And in this section of the course, the flexibility method, which we're covering. So this is flexibility. Now the inverse of flexibility is stiffness. So when people talk to you about the stiffness method, it's just the inverse of the flexibility method. So it's just the opposite way of seeing things. And the flexibility or stiffness methods, these are what go into computers, computer software. So slope deflection method is a great method for a hand calculation, as is moment area and other stuff. When you're using computer software in design offices, which engineers are doing these days, inside the program is the flexibility or stiffness method, and that is a matrix method, and the computer will then be solving a lot of simultaneous equations in order to tell you what your deflections are. So why this section of the course is important. Of course, it's important to do hand methods so that you can check work quickly. It's quite easy to make a mess when you're using computer software, and a hand calculation would help you determine if there's an error in the computer solution. Not so much an error in the computer solution, but more an error in the person who put the problem into the computer software, an error that they could have made. So this section of the course, flexibility or stiffness, remember when you see software, it's going to be this method that has been programmed into the computer package. So self-study, you may use the following for additional self-study. Again, Megson, and then Gear and Timoshenko, some problem sheets at the ends that you can have a look at. Okay. So, table of contents, advantages and disadvantages of statically indeterminate structures, structural analysis using the flexibility method, basic idea and concepts of this method, a degree of statical indeterminacy. So you can use this method, obviously, to solve statically indeterminate structures. Analysis of continuous static indeterminate beams, and analysis of portal frames. And then from there, we can go on to indeterminate trusses, and then finally analysis of statically indeterminate mixed structures. So that would be like the virtual work example that we looked at for the cable and the beam. A mix of a wire with a beam would be a mixed structure. And of course, that problem that we solved here, this problem that we've gone through before, this is a statically determinate structure. Okay.
So everything in this section in the virtual work part has been a statically determinate structure, and the flexibility method will be used for statically indeterminate structures, which is why it's a sort of an extension to the virtual, to the unit load method. Okay. So, example number 1, calculate reactions using a support reaction, using a support release. We'll have a look at that problem in a second. Unfortunately, I don't have a printer at home, so I've not been able to print out the solution. But obviously, it's in the Dropbox. I would have written out a solution in the Dropbox. As an in-class problem. So let's have a look at this one. So step 1 would be to introduce a release. So first of all, let's identify that this is a statically indeterminate problem, and I would say maybe practice this one and solve it with the slope deflection method if you can. So step 1 in this case here would be to introduce a release. In this case here, support release. Okay, so I'm just doing this to try and explain how the flexibility method works in terms of helping you work out that reaction. So I introduce a release and a support release, so I'm going to be removing that release there. Okay, so that means that I'm going to be ending up with this case here. So hopefully you should be able to calculate that. So this is the real structure with a release. So this is a real structure with a release. Okay. Now, let's now have another structure here, which would be another real structure. And this one here, I would draw it out as being the actual problem. With the 100 kilonewtons there. Now, I'm going to say that this problem also real, so this is real, so none of these are virtual, don't get confused by that. So this one here is going to be equal to, using theory of superposition, is going to be equal to this problem here. And onto that, I would be adding this problem here. Okay, I'll just check to make sure that it's within the video, okay? So this is the original problem. I've turned it into a statically determinate problem by removing that release, and then I'm adding that onto something else, and I'm going to be sticking a load here at the end. Okay, so the load that I'll be sticking there is 1 kilonewton. Okay, so at this stage, this is real, and this is real. So all we're doing is theory of elasticity, or theory of superposition, where you can add real things together. So we know that this real beam is going to deform something like that. Okay, so zero rotation here, zero vertical deflection here. There's going to be a vertical deflection here, and the vertical deflection here is going to be zero because of the support. And if I remove the support for my two cases, which I'm going to be adding together to be equal to this, this one is now going to go down like that. So for the terminology that we're going to adopt, which would be explained in the course book, but for now just get used to it. This is delta 1 naught. Okay, so it's delta 1 naught for this deflection. So I hope that you're all okay in that we can calculate that deflection if we wanted to using the unit load method. Okay, now this one here is 1 kilonewton, so maybe that 1 kilonewton may cause a deflection in that direction going upwards. Now, if I solve for this 1 kilonewton, and if I got the deflection here under the 1 kilonewton, then I think you should be able to work out a factor x, where x can be calculated, where it can be multiplied by the 1 kilonewton, such that this deflection is equal, delta 1 naught is equal to x multiplied by what I will call delta 1 1. Okay, so that would be a delta 1 1. Okay. Let me just check the camera, make sure that it's showing. Oops. Okay, so so this is, just to stress again, this is real. This is real as well. This is nothing more than theory of superposition. And if you know this, then you should have enough if you know that deflection calculated using virtual work, and if you know that deflection also calculated using virtual work, then you should be able to say x is equal to delta 1 naught divided by delta 1 1. Okay, and that would be equal, dividing delta 1 naught by delta 1 1, x would then be the reaction at that support. So the reaction at this support here is going to be x times 1 kilonewton. Okay. So hope that's really clear. So delta 1 1 and delta 1 naught and delta 1 1 in this case here are acting in opposite directions. So we can see they're acting in opposite directions, and if you increase this by a factor x, increase 1 by a factor x, we will be able to have a deflection here. So that was 2, then it would be 2 delta 1 1. If it was 3, that deflection would increase by 3 times, and eventually by finding the right factor, you would be able to make that deflection the same as that deflection, in which case the net deflection at that point there is going to be 0. And the way to get that is to divide delta 1 naught by delta 1 1. Okay. So I do remember the first time I saw this, I did find it a bit puzzling, and it did take me a while to have a think, but now it's pretty obvious. But if you're having a bit of trouble, just have a think about it and work through these examples, and it should come out. So Now, if I say x times 1 kilonewton, which would be the factor x, and then you can see that x there would become delta 1 naught divided by delta 1 1. So what we need to do now is to work out that deflection. So to work out this deflection, delta 1 naught, the first thing to do is to plot the bending moment diagram. So we would say, okay, I'll just draw the bending moment diagram here. So I'll just draw the bending moment diagram like that and say that's going to be the bending moment diagram of this portion. So obviously there's going to be no deflection. There's going to be no bending moment in this portion here. Okay, so that portion there is going to be straight. And the bending moment diagram of this portion here, we've got 1 kilonewton at the end, and the bending moment diagram of this one here, so that becomes the tension side at the bottom. The bending moment diagram is going to be like that one there. So we've got our two bending moment diagrams, which we can add together, and later on that will give you, let's just jump ahead, that will just give you the combined bending moment diagram right at the end. So hopefully you'll be able to see that by adding these two together, we'll end up with a bending moment diagram like that later on. Anyway, let's start with step 2. And step 2 is use virtual work to calculate the deflections. So use virtual work to calculate the deflections. So we want to get the delta 1 1. So delta 1 naught, which is the first deflection, is going to be equal to 1 over EI times the integral of the real case here. So remember, all these are real. So the integral of this case here, oops, with the 100 kilonewtons, which would lead to that deflection. And we want to know the deflection at that point. So on that point there, we would be putting on the 1 kilonewton. Okay, so we want to know the deflection at that point. So this one here, this is the first time we've got something that's virtual. So remember, everything here is real, and this is the first time we've got something virtual with the 1 kilonewton. So just put the bar on, in case, and then integrate that as dx. So this is now going to be equal to 1 over EI. So it's obviously going to be from 0 to 10 meters. And we would now need to draw the bending moment diagram. So the bending moment diagram of the first portion is going to be like that. And the second bending moment diagram of this one is going to be this. And this is going to go from 0 to 10 meters. So we've got two shapes that we need to integrate. So on this axis here, I'll say that's 0, that's 5 meters, and that's 10 meters. So that represents 10 meters. And of course, you can acknowledge that since that's 0, everything here is going to be 0 too. Okay. So we effectively are saying, let's integrate that from 0 to 5 meters, because it will work out to be the same, and we just worry about these two shapes here. So let's jump to the appendix to work out the delta 1 naught. And obviously put dx. So this is going to look like shape 4. Okay, so this is going to be shape 4. So I'll put a 4 there. Okay, and now this one here. So if we look at this one here, the 4 is going to be on the bigger side, and we can see that this one here is going to go like that. So I would choose 4, 3. Okay, I'm sorry, I would choose 2, 2, 4. So I would choose that one there, okay, which would be 2, 2, 4. Okay, so you might say, why isn't there a 3, 4? So we can see a 4 there. So you might say, why isn't there a 3, 4? A 3, 4 would be the same as a 2, 4. Okay, so a 3, 4 is the same as a 2, 4, and so it's not shown. Okay, because it would be exactly the same equation. So so having identified the shapes, that's going to be 1 over EI. Okay, and then this one here, shape, so that's going to be shape 2 and shape 4. So 2, 4 is going to be L over 6 A4. So A4 is the big site there. So the big site there is going to be 500 kilonewton meters. Okay, 500 kilonewton meters. So the big site there is going to be 500 kilonewton meters. So A4 is 500 kilonewton meters. And then onto that, I need to multiply that for shape 2, 4. 2 times A2 plus 1 times B2. So that's going to be 2 times whatever value that one's going to be. So, sorry, whatever value that one's going to be. So that's going to be 10 times 10, 2 times 10 kilonewton meters. Just check the camera, can be seen right. 2 times 10 kilonewton meters, and then I'm going to be adding that onto B2, which is going to be on the other side, and B2 is going to be 5 kilonewton meters. Okay, so we've got those lots there, and then the last bit to worry about would be the length. So 2, 4 would be the length of 6. And of course, L in this case here is 5. So I'm going to put 5 meters there, and I'm going to divide that by 6. And if I work out the whole thing, I'm going to get 10420 divided by EI. Okay, and that's the first bit. I've been able to work out my delta 1 naught, and I'm 1 step away from being able to work out the x. So so note that these are linear functions, so they're just straight lines. If you've got any confusion about why I chose shape 2, 4 with two straight lines, as I mentioned in the previous lecture, if you've got any confusion, then don't do it that way. Use 2, 3. Okay, if you use 2, 3 for 2 straight lines, you won't go wrong. So if you've got any confusion as to what to choose, don't worry, just stop and use 2, 3. So 2, 3 is 2 straight lines. So you could have used 2, 3. So that's 2 straight lines. 2 is a straight line. 3 is a straight line. So you can always use 2, 3. and you don't need to use 2-4 as we have done in this case here. So I suppose what I would suggest at this stage is that we stop and that you have a go at calculating delta 1, which would be that deflection under 1 kilonewton. And then you can see, you can divide the two by each other, and you'll be able to work out the reaction at that position there. Okay, so that's what we'll do next time.